Hey guys, welcome to this video in which I'm going to talk about databases and more specifically Relational Database Management System, RDBMS. Basically, I'm going to explain how does RDBMS work. In fact, RDBMS such as PostgreSQL, MySQL, MariaDB and so on, there are plenty of examples. They are really widely used today and among the most complete software architectures in use. They are the result of decades of research and optimization, but yet they are used as black boxes by most users. A quick disclaimer, we are not going to talk about DB design, normalization, and so on, because I think there are already plenty of very good explanation for this on YouTube, and it's not focused on SQL either. That being said, let's move on to the next part. In the first place, why do we need a DB? And when I say DB, I'm talking about database and a RDBMS. In fact, after all, why not just store everything in spreadsheet? Because the reasons for this is that databases coupled with RDBMS are really a convenient way of managing large amount of data. In fact, it would be much more complicated with spreadsheet. Imagine with a lot of rows, the spreadsheet would just become so slow we could not use it anymore. Whereas with the DB, we have plenty of amazing tools to deal with large datasets, like indexing, partitioning, and clustering. Then you can implement checks and constraints quite easily in a database, so you can make sure that your data is correct, something that you cannot do with a spreadsheet, for instance. You can also update and fetch the data quite easily with the DML, such as SQL. You can also ensure data integrity and minimize redundancy, if your database is correctly designed. You can also handle fault tolerance and concurrency and enforce ACID properties. We are going to talk more about this later. Now, let's move on to, there are plenty of other reasons to use a RDBMS rather than a bunch of spreadsheets, but I will stop there. I think you got the idea. And now let's move on how a database is supposed to store data. Before studying the structure of RDBMS, I would like to explain how a data record is stored in a database. We all know the tabular representation of a data record, which looks like this, but it's just a human readable way to see the data. It's not actually stored like this in real life. In fact, each row is stored as a record looking like this. This record is a sequence of bytes split in two areas. So the first one, the green one, stores information about the columns of the record, describing a variable whose length is fixed, like integers, floats, and so on. The second areas, the blue one, does the same, but with columns whose length can vary, like varchar, text, and so on. And so now that's how a record is stored on disk. Let's move on to the next slide. But records, as we just see, need to be organized. Otherwise, it's a mess to compute and it's not efficient. That's why RDBMS store and put them inside what we call pages. A page is a structure of 8 kilobytes, which contains two major sections: the header, right there, and the body, right there. The body stores the data record and the header stores metadata about this page. So how many records are stored in the body, for instance. So now we have pages, but that's still not how a table like this is stored on disk. The table that we know of may be implemented as different data structures, like flat files, heap files, hash buckets, or B plus trees. Actually, pages are stored inside these data structures. If we consider the main data structures in use in RDBMS, we have heap files, which are an unordered set of pages. You also have hash bucket or hash table. To explain briefly, we have a hash function that computes the hash of the page. This page will be stored in the bucket whose hash corresponds to the hash of the page. And lastly, you have B plus trees. They are basically trees of pages, and they are the most common data structure in use in RDBMS because they can do random and sequential access efficiently. That is to say, they can efficiently retrieve either a random page or a sequence of pages. So finally, we found it. Tables are stored as hash tables or B plus trees or heap files, which are data structures containing pages which contain records. And I just wanted to emphasize that depending on which data structure you use to store your tables, the speed of retrieval and the speed of insertion won't be the same. For instance, heap files, they are quite quick for the insertion um, because they are unordered. But they are quite slow for retrieving something specifically. On the contrary, hash table, they are quite quick to find a record, and B plus 3 are also quite quick with the time complexity of O logged n. People often get confused between the RDBMS and the database. Just to be clear, a relational database management system is the piece of software that is supposed to manage, hence the name, that is supposed to manage a relational database. The database itself, that's just the cluster of data. Examples of RDBMS would be MySQL, PostgreSQL, and so on. That's what we'll talk about now, the RDBMS. I will start by giving you a broad overview of what a RDBMS is. RDBMS has 5 main components. They are deeply intertwined and interact with each other. And we'll go through each of them during the study of the query. But first, I will describe them quickly. First, you have the Client Communication Manager, which manages the client connections. And then you have the Relational Query Processor, which reformats, optimizes, and executes the query. You also have the Process Manager there. In fact, databases have a pool of processes and threads to manage in order to process queries. And that's the role of the process manager. It manages the threads of processes with the dispatch and scheduling block and checks if the system has enough resources to actually process the query with the admission control block. And yeah, I forget also there is the transactional storage manager. Basically, it makes sure that the query is executed properly, so respecting the aside properties. And the last one, shared component and utilities. That's the components which don't belong to any particular block, but they are still useful, like catalog manager, which stores the metadata about our database, like the name of the tables, their schema, and so on. Now that we gave a quite broad overview of the RDBMS, we'll go through the life of a query together to see how the different components behave and interact with each other. The first step is the client connection to the client manager. The client calls an API to send the query to the client manager of the RDBMS via the ODBC or the GDBC protocol. Once being called, the client manager performs several tasks. It checks the authentication and checks if the client has the authorizations for querying the database. If the database doesn't have the required resources for a certain period of time, the client manager closes the connection. And lastly, it stores the results of the query in a in-memory buffer before sending them back to the client. At the same time, the process manager, this block, is called and takes care of two things. First, it maps a thread to the query with the dispatcher, so the query can actually be processed. And it performs admission control to make sure the system is not overused. So if there are already too many queries being processed, this query will wait before being sent to the next step, which is the relational query processor. But if everything is okay, the query is sent to the relational query processor. So let's take some time to go through each step of this block. After arriving from the client manager, the query goes directly into the query parser. It carries out several steps, like switching the table names for full names of the form server.database.schema.table. It also substitutes the aliases by this kind of full name. It invokes the catalog manager to check if the table exists in the catalog and that the attribute referenced are correct also. It checks if the query is syntactically correct. So the usage of attributes, the nesting of subqueries, and so on. And our last example, if it checks if the user have enough permissions of the tables. And you have also plenty of other actions that the query parser does, but I won't go through each of them now. And yeah, I wanted to say also, it also converts the SQL statement into a format easier to process, which is known as the parse-tree structure of the SQL statement. You have an example of such structure right there. Then this parse tree is passed to the query rewriter module for further processing. The query rewriter is responsible for pre-optimizing the query before passing it to the query optimizer. For instance, it does what we call view merging. So if you are using a view in your query, it is replaced by the SQL code of the view. It also does constant arithmetic simplification and subquery flattening. To explain a bit, to prevent optimizing too complex queries, most RDBMS rewrite the query in the form select from where block, and they do not optimize across blocks. And this is called the query normalization. And I have an example right there. So instead of having a nested subquery like this, it flattens the query. This way it's easier for the query optimizer to optimize the query. It also removes the unnecessary operators, so you don't have a distinct keyword on a field with a unique constraint, for instance. And it also used the rewriter is actually able to find which partition must be run, which is also very useful for the query optimizer. And again, there are plenty of other ways to pre-optimize a query, but I will stop there. Now that all these steps are done, it will pass the modified parse tree to the next step, the query optimizer. The job of the optimizer is to transform the query internal representation into a query plan for executing the query. So it takes the parse tree we saw before to output this kind of structure, which is a sequence of operators where data goes through. There are many different operators. Here we have heap scan and index scan, which are used to get the data. After you have other ones like group by, sort, or adjoin. So what I want to say is the query plan here is one of the many possibilities for the query plans of this query. It could have taken other operators to the scan, for instance. And therefore, one of the tasks of the query optimizer is to choose which query plan is the best, so the cheapest in terms of resources. To do so, it uses an algorithm based either on dynamic programming or a heuristic, for instance. And this heuristics performs a CBO, so a cost-based optimization algorithm. Basically, this algorithm takes the CPU cost, the memory usage, and the disk I/O as metrics and tries to find the cheapest query plan that is to say the cheapest chain of operators. I gave you an example there. SQLite implements a heuristic to do like the TBO, called the nearest neighbor algorithm. Maybe you've heard about it. And note that we've seen the main goal of the query optimizer, which is to find the best query plan. There are actually other ways used by the query optimizer to optimize the query, like for instance deciding how to parallelize the operators, or perform autotuning. An example of autotuning, it's a really interesting field. An example would be to compute the cost of a query and compare it to the cost if we had an index for this table. If the cost is much cheaper, the RDBMS would automatically create an index to compute the query. I wanted to go through something else. The query plan chosen also specifies the estimated cost of the query in terms of disk I/O, memory footprint, and CPU load. How does the query optimizer know it? Actually, it computes, like the RDBMS computes statistics regularly for each table. For instance, when I'm talking about statistics, I'm talking about most frequent values, average, quantiles, and so on. With these statistics, it can find the estimated cost of the query that we've just talked about. And these statistics also help the query optimizer to find the best query plan. So if the statistics are not up to date, the query plan will be badly optimized and the query will take a lot of time to execute. At this stage, there is another intervention of the admission control block, which decides based on the estimated cost of the query, done with the statistics, if the query should wait to be processed or not, depending on how much resources there is left. But if the admission control is passed, our optimized query plan is passed to the query executor to run it. So the query plan is executed by the query executor, and to execute it, the query executor invokes the procedures for the operators that we've talked about before. These operators can be table access, like index scan, file scan, and so on. And they can also be query execution algorithms, so nested loops joins, hash joins, merge join, and so on. They also can be executed in parallel or in sequence. It's up to the executor to decide. I wanted to make a quick point on access methods. The access methods are our way of accessing the data from disk, to be brief. Then the access methods get the data from the transactional storage manager that we will see in the next part. So they take the data from it and pass it to the next operators of the query plan. And the next operators will complete the result, and the result will be returned to the client manager. Now we'll see how the query executor communicates with the transactional storage manager to get and write the data. So in terms of components, the transactional storage manager is composed of 4 main components: a log manager for concurrency control, a log manager for recovery, a buffer pool for staging data from disk, and the access methods we've just talked about for organizing data on disk. Examples of transactional storage manager that you might have heard about would be like InnoDB or MySM for the RDBMS MySQL, for instance. So, in practice, and very simply put, the transactional storage manager is used to get and write the data in a nested compliant manner. That is to say, the transaction must be atomic. So all the transactions actions are committed and entirely done or not at all. There is no middle ground. They also have to be consistent, and transaction must leave the database in a consistent state depending on the state of constraints. And the transactions also have to be isolated from each other. So like concurrent transactions cannot see each other while ongoing and while running. When I say see each other, it means that they cannot see the actions of the other transactions. And they also have to be durable. So the durability of the ACID property is actually, it guarantees that the updates of the committed transactions will be visible in the database. But we just said in the slide before that the query executor is supposed to fetch the data from the transactional storage manager, but from which part? Actually from the buffer pool. And first, I want to address the question, what does the query executor need to compute results? It needs the records, which are stored in pages, and these pages are on disk. But if the query executor would pick up the pages from disk one by one, it would be very slow, since the disk I/O is quite a bit bottleneck in terms of speed. Therefore, the transactional manager uses an in-memory buffer used to load the data from disk before giving it to the query executor. This buffer is called the buffer pool, right there. It speeds up the database dramatically. And this buffer pool is managed by the buffer manager module of the storage manager. Next point, a query is computed by chunks of data. So when the query executor is processing its first chunk of data, it will ask at the same time the buffer manager to preload the second bunch of data to prevent the query executor from writing. This is what we call prefetching. But another problem of the buffer pool, it's that the buffer pool has a limited memory, and loading and purging the data from the buffer pool is costly in terms of disk I/O. So the replacement of the pages by the buffer manager must be really efficient. To do this, most databases use a LRU algorithm. So LRU stands for least recently used. The idea behind the algorithm is quite straightforward. It keeps the data that has been used recently in, and it discards the oldest data from the buffer pool. There are also other buffer replacement algorithms like 2Q, clock, MRU, and so on. But they are quite similar to LRU actually. So so far all we have talked about was, sorry, yeah, that's this one. So far all we talked about was a read buffer, but there is also a write buffer where pages that are supposed to be modified are loaded in to be modified by the query executor. If we did not use a write buffer, the query executor would write the pages one by one on disk, and it would be very long. It is much more efficient to store the pages in memory and fetch them to disk by batch. Once a page has been modified by a query, it is called a dirty page. Quite common there. Quick comment, sorry. This write buffer is also handled by the buffer pool as the read buffer we just saw. This time it manages when the pages stored in the buffer are flushed to the disk. So the query executor can now read and write pretty efficiently from the database by using the buffer pools as interfaces with the disk. But these transactions have to be ACID compliant, as we saw before. And these properties are assured by the rest of the transactional storage manager, like we're gonna see right away. Let's say that several users are running multiple SQL queries, SQL queries to create, update, and read data. The problem begins when two transactions are using the same data. Indeed, if a transaction is modifying data, we must find a way to prevent another transaction from interfering. Otherwise, it breaks the isolation property of the ACID transaction, for instance. And this problem is what we call concurrency control. So how to implement concurrency control? There are several ways to do it. I listed the two main ones. down there. The first one is strict two-phase locking. Transactions actually put a shared lock on every data record before reading it. It means that it allows read transactions but blocks write transaction. And afterwards, it can also put an exclusive lock on every data on every data record before writing it. And this lock, the exclusive lock, allows neither for a read transaction nor a write transaction. And all locks are kept until the end of the transaction. And the second way of implementing concurrency control is the multi-version concurrency control. And in this implementation, transactions don't enforce locks but are guaranteed a consistent view of the database at some time in the past, even if rows have changed since. In practice, DBMS usually implements concurrency control via two-phase locking, the first option right there, and some DBMSs support a multi-version concurrency control as an add-on. So the concurrency control is implemented by the lock manager that we see right there. The lock manager has two main functions. The lock function, which locks a resource in a certain mode for a certain transaction, so other transactions cannot access it. And the unlock function, which unlocks all the resources are harnessed by a transaction once the transaction is done. To support its job, the lock manager maintains two data structures. The first one is a global lock table, and it's maintained to hold the lock names and their associated information. And the second one is a transaction table, which contains a pointer to the DBMS thread state and a list of pointers to all the transactions lock requests in the lock table. It facilitates the removal of all locks associated with a particular transaction. A quick comment here. Database management system can use a different granularity of locks. So locks on rows, pages, partition tables, and so on. Now that the concurrency between two transactions is being taken care of by the log manager, now we will see how this apply to the isolation property of the ACID transactions. So if two transactions A and B run at the same time, the result must be as if A finishes before or after or during transaction B. It shouldn't matter. That's the isolation, and it's implemented by the log manager, as we saw in the previous part. There are several levels of isolation depending on how isolated we want our transaction to be. The more isolated our transaction are, the more logs we use. The question is why the hell would you want several levels of isolation? Because the transaction will waste more time waiting for the logs. This is why most of the RDBMS don't use the highest level of isolation, which is serializable per default, because it takes some time. So if you need your query to be processed quickly, the highest level of isolation might not be the best idea. And RDBMS in use today, like PostgreSQL, MySQL, and Oracle, use a mix between lock and data versioning to implement isolation. They give the choice to the user between several levels of isolation listed below, like read uncommitted, read committed, serializable, and there are plenty of others like snapshots and so on. So isolation has been taken care of by the log manager. Let's move on to the next ACID property, which is consistency. Consistency is quite straightforward, this one. It doesn't depend on an element of the transactional storage manager. It is implemented by runtime checks of the query executor to see if the transaction actions will violate a SQL integrity constraint, like for instance primary key or foreign key constraint. For a refresher, foreign key constraint enforces a referential integrity, which essentially says that if a column like value A refers another value, this value must exist. Otherwise, it violates the foreign key constraint. So the query executor is supposed to prevent this kind of problems. In this way, the database will always be in a consistent state. Now let's move on to the next ACID property, which is atomicity. And if atomicity is about if the transaction is not committed and is aborted ongoing, the database must come back to the original state before the transaction started. In other words, it has to roll back the transaction. There are multiple reasons why a database would have to roll back a transaction. For instance, because the user cancelled it, because the server crashed, because the transaction broke the data integrity of the database, like a transaction which has duplicates in a row with the unique constraint, for instance. And how does the database management system plan to do it, to implement atomicity? Well, the DBMS uses a write-ahead logging protocol, which consists of 3 rules. The first one is each modification of a database page should generate a log record, which should be flushed to the log device before, and that's very important, before the database page is flushed to disk. Secondly, the database log records must be flushed in order. And lastly, concerning the transaction commit request, a commit log record must be flushed to the log device before, and that's again very important, before the commit request returns successfully. The actions of a committed transaction can be redone after a system crash if they are not yet in the database. So this is the ARIES algorithm which implements and which takes care of that, and it actually implements an enhanced version of the whole algorithm, the whole protocol, and it's more or less used by all the RDBMS today. But what's going on in practice? For each page modification in the write buffer, a log is generated by the log manager. Then this log is written to the transaction, which is a disk like RAID, for instance, a RAID disk, which is really safe. The log is composed of several things. First one is LSN, which is a unique number given to the log. This number is the chronological rank of the log. The transaction ID, so the ID of the transaction that produced the operation, the page ID, which is the location on disk of the page, prev LSN, which is a link to the previous log record produced by the same transaction, undo operation, which is a way to remove or reverse the effect of the operation, the redo operation, which is a way to replay the operation. So in case of abortion, the DB will know how to redo or undo the unfinished transaction by reading the logs which are still present in the log buffer. That's how RDBMS ensures atomicity. And the last but not the least, durability. It has 2 characteristics. First, it guarantees that the updates of a committed transaction will be visible in the database, even if the database crashes. And if a transaction log is flushed to the disk, but the system fails before the data could be written on the disk, then that data will be updated once the system springs back into action. In fact, if the server crashes when the transaction is being committed, we lose the data in the memory pool, so the data about to be flushed will be lost. So a crash recovery only needs to rebuild the in-memory data structures, like the buffer pool, for instance. And this is also ensured by the log manager. But first, let me have a quick comment on the background process called the checkpoint. The purpose of the checkpoint is to flush dirty pages in order to keep the number of transactions that have to be rolled forward during a potential recovery to a minimum. When a checkpoint happens, the dirty pages get flushed to the disk, and the RDBMS registers the LSN of the transaction at the same time. This will serve us for the recovery phase that we'll see really soon. As I just said, the checkpoint updates the last LSN registered. To fetch the dirty pages back, we go through all the logs from the last registered LSN on disk. It means that we go through all the logs since the last checkpoint, and not just all the logs on disk, which will be very long. We can do that because the logs corresponding to the committed transaction, but which are not flushed, would have a LSN greater than the LSN registered because they are more recent. So in a nutshell, there are 5 main steps. The query executor asks for a modification of a page located in the buffer pool to the cache manager, that's the cache manager, but that's the buffer manager in our case. The log manager stores the log associated to the modification in its log buffer. At this step, the query executor considers the operation done and go ask for more tasks. And then the log manager writes the log on the transaction log disk. Then the cache manager, the buffer manager, writes the modification on disk. And a transaction is finally committed when all these 5 steps are done for every operation in the transaction. Now, the transactions can be done properly, and we can go and summarizing the journey of the query with these next steps. The client sends the query manager to the client manager, that's the first one. The query is then passed to the relational query processor by the client manager. This query is optimized into a query plan. The query plan is then executed by the query executor, which modifies received data from the transactional storage manager. While the query is being executed, the transactional storage manager makes sure it is executed in an ACID compliant way, as we just saw before. Then the query executor returns the query result in the client manager buffer. Once the log of the transaction has been flushed to disk, the client manager sends the result to the client. And finally, the RDBMS thread associated with the query is now ready to parse another query. And before finishing this section, I would like to point out that each RDBMS has a different implementation. For instance, each RDBMS can have different algorithms to optimize the query plan. So a lot of components that have been quoted above, but we've been through a lot of components, but not all of them. There are a lot of other utilities like the memory manager. So the RDBMS allocates a huge amount of memory for other tasks than just the buffer pool. And the correct management of this memory is a performance issue. For instance, query operators like hash joins or sorts need a significant memory at runtime. There are also replication services to replicate a database across network. The backup export utility to export the database somewhere else, the bulk load to ingest massive amounts of data in one shot instead of one row at a time, which is much faster, and monitoring. So for instance, if a query consumes more resources than wanted, most DBMS provide tools to assist admins to observe this kind of problems. That's all, guys. I just wanted to do a quick comment about this video. This is really a broad overview of what RDBMS is doing, and there are many more topics to talk about, like the hardware architecture of RDBMS. I also listed some additional reading if you want to. Thanks for watching the video. Let me know in the comments what you've thought about it, and your feedback is really important to me. All right, see you guys.